Hello everyone. Today we're going to be talking about factored form of quadratic relations. The x-intercepts, the zeros. This is the information that we can determine when we factor a standard form quadratic into factored form. Okay, so let's start with the first example. And in this case, we're going to common factor. So the starting quadratic is y equals 2x squared plus 6x, and this is in standard form. We notice there's a common factor of 2x in each term, and when that gets factored out of the equation, in other words, we are dividing both terms by 2x. The result is 2x brackets x plus 3. And this is factored form. So we went from standard form to factored form. Then we could take each factor and set them to 0. Because when y equals 0, we are on the x-axis. And if we're on the x-axis, then we have found an x-intercept. So the first x-intercept is 0, 0. And the second one's at -3, 0. And that's why the nickname for the x-intercepts of a quadratic is called the zeros, because y equals 0. And let's analyze this a little further. A in standard form is 2, b is 6, c is 0. And a equals 2 tells us that the quadratic opens up, and c being 0 tells us that the y-intercept is 0. And I plotted the x-intercepts, I plotted the y-intercept, and I drew the parabola going upward since a is positive. Can we determine the vertex from this information? The answer is yes. If we start with the axisymmetry, which is an h value that equals r plus s divided by 2. R and s are the x-intercepts. So in this case, -3 plus 0 over 2. And that leads us to h being -1.5, which is the x-coordinate in the vertex. If we take that x value, sub it back into the original equation, we can determine the y value in the vertex. In other words, the k value. H comma k is our vertex. And in this case, when we substitute the -1.5 into the equation, we determine that the y value is -4.5. And thus the vertex has been completed. And when we go back to our graph, and we plot the axisymmetry, which is the symmetry, the mirror down the middle of this parabola, at -1.5, and by calculating the y value, we determine that the y coordinate is -4.5, so altogether our vertex is in the middle of these two branches at the lowest point. Since a is positive, we're going to have a minimum, so the minimum value is -4.5 for this parabola. It occurs at an x value of -1.5, and together that forms your vertex. -1.5, -4.5. Okay, that concludes common factoring. Now, let's look at the big picture. When we go from standard form into factored form, all this information can be determined. These are the key features, the key characteristics for quadratics. The x-intercepts, which are the r and s values, nicknamed the zeros. The y-intercept, which is the c value. The direction of the opening, which we can determine from the a value, positive up, negative down. And the axisymmetry by getting the midpoint of the x-intercepts, which is h. Then subbing back into the equation, we can determine the k value, which completes our vertex. Okay, let's move on to the next example. What's the big picture for factoring quadratics? Well, the big picture is All these factoring strategies is the skill, and then applying that skill to quadratic relations allows us to answer more problems and situations involving quadratics, parabolas, quadratic relations. So let's move on to the next example, the next technique for factoring. And we talked about decomposition in another video, but in this video, let's further examine decomposition, but in a different way, using an idea of product and sum. So if we consider the first term, x squared, the factors are x times x. And if we consider the last term, 16, we can go with factors of 2 and 8. And when you multiply x times 2 and x times 8, you end up with a decomposition of 10x. 2x plus 8x equals 10x. So we've decomposed 10x. But this technique uses decomposition in a slightly different way. We go towards 10x instead of going backwards from 10x. So we determine factors of the first term, x times x, factors of the last term, 2 times 8. Then we see if the product of those terms equals 10x, and in this case they do. So we take the first term's factors and we write them first in our equation. And we take the last term's factors and we write them second in our binomials. And as such, we have factored form. Now we could check that. We could expand this factored form like you did in previous chapter of quadratic relations when we were expanding factored form into standard form. And as you could see, the expansion, the first term, then into the second term, and then the second term with the first term, and then the two last terms, ends up equaling that standard form that we started with. So this technique of product and sum with decomposition helps us factor. And then once it's factored, like the previous example, we could find all the key characteristics. Okay, let's consider another example. Okay, so we have y equals 3x squared plus 21x plus 36. You might notice there's a common factor. So let's divide that out, and we're left with x squared plus 7x plus 12 in the brackets. And if we use this product sum technique, we can determine that our factors become x plus 3 times x plus 4, along with the original times 3 combined. This all becomes our factored form. Y equals 3 brackets x plus 3, next bracket x plus 4, and we've gone from standard form to factored form using common factoring and then product and sum. Okay, let's consider another example. Let's consider when a is not 1. So factoring the trinomials when a is not 1. And let's use an old skill of expanding binomials to further understand the product and sum technique when a does equal 1 or when a doesn't equal 1, like in this case. So let's take factor form. Let's take y equals 2x plus 3 in one bracket, one binomial, and the other binomial is x minus 7. Let's expand that, and we have standard form 2x squared minus 11x minus 21. You might notice that there's no common factors. The 2 doesn't divide all the terms, the 11 or the 21 doesn't divide all terms, and the x can't divide all terms. So we don't have common factors here. So we need to move right into product and sum or decomposition. I'm suggesting in this video versus the other video to use product and sum with decomposition. And we take the first term, 2x squared, and factor it to 2x times x in blue. And then we take the last term and factor it to negative 7 and 3 in green. There's other factors, of course, but start with one pair and see if you could work backwards and decompose the negative 11x. So when we multiply those factors, we end up with products of negative 14x and 3x. And you notice when you add them, it equals the negative 11x. So we've decomposed that negative 11x with these products and sums which allows us to go straight into our factors. The blue 2x and x factors go first, the green -7 and 3 factors go second, and we have just went from standard form to factored form. And when you look at the big picture, when we started with expanding first, those were the factors that we started with. On the very first line here, the 2x plus 3 binomial and the x minus 7 binomial. So we went from factored to standard, and then from standard back to factored, using this idea of product sum with decomposition. Okay, let's move on to the next example. These now are special cases for factoring. Special cases. In this case, you might notice that the bx is not in the quadratic, therefore b is 0. And when b is 0, we have a special case. The first term of x squared and the last term of +9, you might notice are perfect squares. So we're looking at a trinomial with bx being 0, so it's no longer a trinomial. There's just two terms. And what are those two terms? Perfect squares. And what's happening to those two terms? They're being subtracted. So you're looking at a difference of squares. We could use the product and sum technique, but we could also go straight into the factors using this idea that they're perfect squares, which means they have perfect roots of x and 3. So write those both in each bracket, and in order for bx to cancel and eliminate and be 0, one bracket needs to be addition and the other bracket needs to be subtraction. Okay, let's look at another example. So bx equals 0, which means we have a difference of, and if you examine closer, perfect squares. 4x squared has a perfect square root of 2x, and the square root of 81 has a perfect square root of 9. So we have a difference of squares. Take the square roots, write them in both brackets, make one addition and one subtraction, and you have eliminated b to be equal 0, which leaves you with a difference of squares. Factored form. Okay, let's look at another special case. In this example, we have a bx. And if you examine all the values, a is 1, b is 6, and c is 9, you might notice that half of 6 is 3, and 3 squared is 9. So there's a relationship here between the bx and the c. And when the relationship is like this, where b divided by 2 squared equals c, then you have a perfect square trinomial. In this case, it's a trinomial, not a difference of squares, because all three terms are present. And if you see up above in the red, where I used product and sum, the factors become x and x for the first term, 3 and 3 for the last term, and they add up. Those products add up to 6x. So we could use product and sum and have factors of x plus 3 times x plus 3, and noticing that they're both the same. Both factors are the same, which means this was a perfect square trinomial, which means we could have avoided all these steps by going straight into our factors. Take the factors, the perfect square root of ax squared, and take the perfect square root of c, and it's an addition because the middle term bx does not eliminate, it remains. So it becomes x plus 3 squared. And notice that bx is positive 6, and in our perfect square roots, it's positive 3, x plus 3, because this pattern is going to lead to another pattern, which we'll see in the next example. Okay, let's move on. And now we have 12x squared minus 60x plus 75. You might notice that they're all divisible by 3, so let's divide out that first factor. Then inside the brackets, you might notice that 4x squared is a perfect square root, and 25 is a perfect square root. And when you multiply the 2 and the 5, you get 10. And when you times 10 by 2, you get 20. But in this case, it's subtract 20. So then we have to consider the other perfect square root of 25, which is negative 5. So the square root of 25 could be positive 5 squared or negative 5 squared. So in this case, we need to go with negative 5 because bx is a subtraction. And that's the pattern I was referring to in the last example. So we have our factor of 3 on the outside of the bracket. We have our perfect square roots of 2x minus 5. And we could square it because they're both the same, which makes the inside of the brackets a perfect square trinomial. And since b is negative, we make our bracket and our perfect square root factor also negative. Okay, let's move on to another example. So in this case, there's no common factor between negative 20 and 25. And since it's subtraction, the perfect square roots of 2x and 5 need to have a subtraction in the binomial. And because it's negative 20, we have a negative 5 in our bracket. And if it was positive 20, we'd have a positive 5 in our bracket. So this is the shortcut for perfect square trinomials, where we don't need to do product and sum or decomposition. We notice that ax squared is a perfect square. We notice that 25 is a perfect square. And since b is negative, we write our binomial with a subtraction. And since in the blue case, b is positive, we write our perfect square root with an addition. Okay, let's move on. Let's do one more example of this with a being 1 in this case. So we have an a value of 1. Okay, let's continue. So we have another example here of a perfect square trinomial, but in this case, a equals 1. In the previous cases, a did not equal 1. So we notice that the first term has a perfect square root of x. We know that the last term has a perfect square root of either positive 4 or negative 4. And since our b is positive 8, we're going to use the positive 4 square root. And thus our brackets become x plus 4 times x plus 4, or x plus 4 squared. And in the case of a negative b, we notice x squared is a perfect square. We notice that 25 is a perfect square. But since b is negative 10, then we go with the negative square root of negative 5. And our brackets become x minus 5 times x minus 5, which is simplified to x minus 5 squared. So we're going from standard form to factored form, but because it's a perfect square trinomial, we have this shortcut. And in general, that shortcut looks like this with a and b variables. The positive 2 tells us we have a positive in our binomial brackets, and the negative 2 tells us we have a negative in our binomial perfect square root brackets. Okay, let's move on. One final example. We have, again, a common factor. B is negative 60. And then in the bracket, it's negative 20. So this is our negative 5, 2x minus 5 squared times 3 factored form from a previous example. And then when it's positive, that's going to lead us to having a 3 times 2x plus 5 binomial bracket squared. Okay, so in general, what are all the strategies for factoring quadratics? All the strategies. Common factoring is always your first approach. Then when a is 1 and you have a trinomial, either use the decomposition method from a previous video or this more efficient technique in this video of product and sum, working towards decomposition. And then strategy 3, when a is not 1, you'll notice that this technique doesn't change. It's the same technique. That's why it's more efficient. So step 2 and step 3 is irrelevant if a is 1 or not. Prior techniques with decomposition, we needed to analyze it differently when a was 1 or a isn't 1. This works in both cases, the product and sum technique. And finally, we have special cases. We might have difference of squares, we might have perfect square trinomials, and then there's some further shortcuts, as already outlined. What does this all allow us to do? What does factoring standard form of quadratic relations into factored form, converting from standard form from previous chapters to factored form in this chapter, allow us? What does it reveal to us? What information is shared? Well, first, the x-intercepts are discovered. The y-intercept can be discovered from the standard form, the c value, and the x-intercepts are discovered in the factored form, the r and the s values. The a values in both forms, and that helps us with our direction and our opening, our max and min ideas. The midpoint of the x-intercepts reveals to us the axiosymmetry, which is the x-coordinate in the vertex. And substituting that x-coordinate or h value back into the original equation helps us calculate the k value, which is the y-coordinate in the vertex. So overall, x-intercepts, y-intercept, direction, midpoint of the x-intercepts, maximum or minimum value, which leads us to the vertex. So the x-intercepts, the y-intercept, and the vertex, we have ordered pairs to plot and graph the quadratic. This can help us in graphing, much more efficient than using another method of table of values and determining a predetermined amount of points until we discover that it's a parabola. In this case, we know it's a parabola because it's quadratic, because it's a degree 2 equation. We can go straight into factoring, which takes us into gives us our x-intercepts and leads us to our vertex, and we have enough information to graph. Once we discover it's degree 2 is when we can continue into this more efficient process of factoring, which leads us to all the information about the parabola. And then with all this information about the parabola, about the quadratic relation, we can apply all these characteristics to solve any interesting quadratic relation word problem that they present to us. That concludes this video. Thank you for watching today. You guys are awesome. Have a great day.